And now much more about gases. Before we can start talking about gases, we have to keep in mind temperature. We are always going to use what's called absolute temperature or temperature in Kelvin when we work with gases and when we work with these gas equations. So Fahrenheit is not something we usually use in science, but we do usually hear Celsius. For every single one of these problems, you're going to have to be converting your Celsius degrees into Kelvin. And we do that by adding 273. And none of these problems will work correctly unless we convert everything to Kelvin. Pressure is something we're also going to have to keep in mind. That's another variable we're going to be working with. Because gas particles are constantly in motion, and these particles are zooming all over the place, and they're bumping into each other, and they're hitting the side of the container, they exert a force when they hit the walls of the container. That force is measured over a certain area, and we call this pressure. Pressure is measured in several different units, so we're going to have to be paying attention to these units. 760 millimeters of mercury is known as standard atmosphere or standard atmospheric pressure. And 760 millimeters of mercury is equal to then 1 atm. This is also equal to 101.3 kilopascals, which is equal to 760 torr. When we do these problems with our calculator, we're going to have to pay attention to these units. And then finally, the last thing you have to remember when you're doing these problems is what is standard temperature and pressure. Sometimes it's abbreviated ATP or at ATP. Standard temperature is 0 degrees Celsius or 273 Kelvin. Standard pressure is 1 atm or 101.3, and this has 25 kilopascals, but you can go ahead and just leave it at 3 if you feel like putting that into your calculator. So those are the variables that affect gases. We've got pressure measured in millimeters of mercury, atm, kilopascal, or torr. We've got temperature, and I told you every single time we do this, we're going to have to use Kelvin. And then we're also going to be affecting volume. Volume is measured mostly in milliliters, but sometimes in liters. And then finally, we're not talking about this one today, but N stands for the amount of gas or the moles of gas. The formula that we're going to be using is called the combined gas law formula, and this is kind of that magical formula. It says that the pressure initially, the volume initially, divided by the temperature initially, will equal the pressure after some change has happened. It'll have a new volume, and it will have a new temperature. You can think about this equation as this. This usually helps a lot of students if they're not great with math. I basically just cross multiplied to get this. And after you see these problems worked out, this should make more sense. The combined gas law is a combination of 3 laws: Boyle's law, Charles' law, and Gay-Lussac's law. Boyle's law is the relationship between volume and pressure, Charles' law between volume and temperature, and Gay-Lussac between pressure and temperature. Boyle's law says decreasing volume increases collision and increases pressure. You can see here as I put this weight on the top and I decrease the volume, watch the pressure gauge, the pressure increases. And you can see that by the collisions on the side of the container. Now, Boyle's law in real life, there's a lot of real life applications, but here's one to look at. Here's a bicycle pump. It works similar to a syringe. When the handle of the pump is pushed down, the pressure inside the pump will increase. In other words, the gas inside is compressed and the pressurized gas is forced inside of the tire of the vehicle. So let's go ahead and get started at a problem here. Here is Boyle's law, and as you read through Boyle's law, it will tell you a relationship between volume and pressure. So if we look at the combined gas law has volume, temperature, and pressure. So all we do is start collecting our data. A sample of oxygen has a volume of 150 milliliters when its pressure is 0.947 atmospheres. What will the new volume of the gas be if the pressure is increased to this? So when you go ahead and use the combined gas law formula, you can see here that it says nothing about temperature. So you can kind of forget about temperature as we're working with this because we're assuming that the pressure or the temperature is going to stay constant. So the first thing that we do is we collect our variables. P1 V1 equals P2, V2 equals. Pressure 1, the initial pressure is 0.947 atmospheres. The initial volume is 150.0 milliliters. The new pressure, the pressure is being increased to this. And then the question is, what is the new volume? So we can go ahead and use P1 V1 equals P2 V2. We have to solve for V2, so I'm going to divide by P2 on this side, divide by P2 on this side. This will cancel out. I end up with a new formula. I like to rewrite it to say V2 equals P1 V1 over P2. And then I can go ahead and substitute all of these numbers in. Now you're going to need your calculator. So when you're working with these, I suggest you just, you don't rewrite them. Some people like to rewrite them. I think this is enough, but if you choose to rewrite them, that's up to you. So I put it right into my calculator, 0.947 times 150. And you can put the 0.0 or not. You're kind of wasting your time if you do. It's more for sig figs, which I'll show you in a second, divided by 0.987 equals, of course, this big long number. And this is where sig figs count, right? So I get a V2 equals 143, but I want to check my sig figs. It's 143.920, blah, blah, blah. But up here I can see I have 4 sig figs, here 3, so my answer should only have 3 sig figs. So my final answer should be 144. And I want to make sure I put my units after that. The units that I use up here are going to be the units that I use down here. So this is milliliters. So that's my final answer. I put a box around it, and that's kind of everything I'd like to know. So that's an example of Boyle's law.
Charles' law is the relationship between temperature and volume. As I heat a gas up, the volume will expand. Charles' law says that heating a gas will cause it to expand by a certain fraction. So if you could look at that image below, it shows how adding heat makes the molecules move faster, hit the sides of the lid with greater force, and then moves the lid up, which increases the volume. The opposite is also true. Volume affects temperature. If you think about Charles' law in everyday life, this is what makes a hot air balloon rise. Heat is added to the air, and the air molecules move faster and further away from each other and cause it to expand. Also, turkey thermometers work with Charles' law. So it has to do with the gases inside the turkey moving around more and causing the thermometer to expand.
Let's move along here to an example of Charles' law. It says a sample of neon occupies a volume. So we have a V1 of 752 milliliters at a T1 of 25 degrees Celsius. But I told you that 25 isn't going to work. You need to always add 273 and convert this to Kelvin. So 273 plus 25, we get 298 Kelvin. So never put that Celsius temperature in. It will end up wrong. What will the new volume be, the V2, question mark, if the temperature is raised to, and you don't have to show this every time, 50 plus 273 equals 323 Kelvin. So as we're doing Charles' law problems, you can see here it says the pressure remains constant. So you can kind of cross out pressure and you're left with V1 over T1 equals V2 over T2. So that's what I'm going to go ahead and use in my equation. V1 over T1 equals V2 over T2. I want to show you some things because some people get really confused with the algebra. In order to get T2 off the bottom, I need to multiply by T2. That cancels. Multiply by T2. And if I were to rewrite this, it would be V2 equals V1 T2 over T1. But I also have this, or think of it this way up here, and I have this to help you if you get confused with algebra. So you can cross out the pressures, and again, you get V1 times T2 equals V2 times T1. And I want to get V2 by themselves, so divide by T1, divide by T1, and you're going to end up with that same thing, that V2 equals V1 T2 over T1. Go ahead and plug your numbers in to the calculator. Now you don't have to rewrite this. We get 752 is our V1 times our T2 in Kelvin, 323, divided by T1 or 298. So my V2 is going to equal 815.087. And again, I'm kind of showing you this for the sig figs. Go back to your original problem to figure out sig figs. Now this gets a little bit interesting because we have 3 sig figs here, but it looks like we have 2 sig figs and 2 sig figs. But after we add the 273, you'll remember we actually have 3 sig figs. So my answer should have 3 sig figs. It should be 815, and my volume is in milliliters. Now, according to our kind of rules, you can be within 1 sig fig, so don't panic if you didn't get that little addition problem there.
And the last one is Gay-Lussac's law. It says that if you keep the volume constant in a closed container and you apply heat, the pressure will increase. And you can see here this has a constant volume, we're adding heat, and the pressure is in fact increasing. If we take away the heat, if we remove the heat, the opposite will happen. The molecules will move more slowly and the pressure will decrease. Gay-Lussac's law happens in everyday life. You can think about a pressure cooker. Basically, it helps you to cook food at a higher temperature because you keep a constant volume.
Moving along, here's an example of Gay-Lussac's law. The gas in the container is at a pressure of 1,500 millimeters of mercury at 25 degrees Celsius. What would the pressure of the gas be if its temperature was raised to 75? Now, in this case, we're assuming we have the same volume of the container, so you can cross out the V's. We're not going to use those. And we can collect our data. So we have an initial pressure of 1,500 millimeters of mercury, and that's 2 sig figs, by the way. Initial temperature of 25, but again, we're not going to do 25. We're going to do 25 plus 273 is going to equal 298 Kelvin. What would the new pressure be? Question mark. If the temperature is raised to 75 plus 273, and if you can do that in your head, that's fine. 348 Kelvin. So I can use either of these equations I want to use. I'm going to skip kind of down to this easy equation. I'm going to say, fine, P1 times T2 equals P2 times T1, and I want to get P2 by itself, so divide by T1, divide by T1. Rewriting it, I get P2 equals P1 T2 over T1. The nice thing about rewriting this out is that I don't have to do this every single time if I have a worksheet or a test that has the same question type on it. So I put this into my calculator. I say 1500 times 348 divided by 298. That's the T1. And I get 1,751, but I know from my sig figs here, I've got two sig figs here, so I want my answer to have two sig figs. So P2 is going to equal 1800 millimeters of mercury, and that will be my final answer that I will put down on my paper. Now, sometimes you have to do what's called the combined gas law, which means we're going to use all of these variables. The pressure, the volume, and the temperature are going to change. So in this example, we've got, I'm going to collect the variables. A sample of krypton is contained in a 200 milliliter syringe. So that's a volume at a temperature of 25 degrees Celsius or 298 Kelvin and a pressure of 120 kilopascals. It says, what will the pressure be? So my P2, I don't know. If the gas is compressed, so the new volume is 150 milliliters, and it's cooled, it has a temperature of 0 degrees Celsius or 273 Kelvin. Remember, 0 plus 273 is 273. So now I want to use the combined gas law. And like I said, this is where this one comes in handy if you're not great at algebra, because in this case, I need to get P2 by itself. So writing this out, I get P1 V1 T2 equals P2 V2 T1. So in order to get P2 by itself, I divide by V2 and T1, cross that out, divide by V2 and T1. I end up with P2 equals P1 V1 T2 divided by V2 times T1. So I can go ahead and plug this all into my calculator, kind of in one shot here. I get P1 is 120 times V1, 200, times T2, which is 273. You can see here where the 0 would have caused the problem, because now I'd be sitting at 0, and that wouldn't work real well for the math. And then I hit divided by the V2, 150. And then I'm going to hit the divided by button again, because I don't like to use parentheses, 298. So if you use parentheses, that's fine. I just like to save myself buttons on the calculator. So thinking about sig figs, it looks like if I wrote this down correctly, this has two sig figs. Let me double check up here. Yes, I did write it down correctly. So my answer is going to have two sig figs. So the P2 is going to equal 150, and that's kilopascals for my P2. And that's the answer with the correct number of sig figs. Okay, one last question here. One more combined gas law problem. I'm going to go ahead and collect my variables. So I've got 1,600 liters. I'm going to call that V1. 1,600 liters of nitrogen are contained at 50 degrees Celsius. Remember, 50 plus 273 equals 323 Kelvin. And it has a pressure of 1,100 millimeters of mercury. What will the volume be, V2 question mark, at STP? So this STP here has a lot of information in it. STP, remember, is 0 degrees Celsius and 1 ATM, but neither of those units work, so I need to make sure that my units match. So my temperature is going to be in Kelvin. So it's going to be 273 Kelvin. And my pressure, I can't use 1 ATM, I've got to use millimeters of mercury, so I've got to use 760 millimeters of mercury. Make sure everything matches up correctly. I'm going to go ahead and rewrite this. P1 V1 T2 equals P2 V2 T1. I've got to get V2 by itself. Divide by P2 and T1. Divide by P2 and T1. I've got V2 equals P1 V1 T2 over P2 T1. Putting this into my calculator, P1, 1100 millimeters of mercury times V1, 1600 times T2, 273 Kelvin, divided by P2, 760 millimeters of mercury. And like I said, I hit the divide by button again for that T1, 323. And then I have less buttons to press on my calculator. Sig figs, we've got 4 sig figs, 3, 4, and you do not need to worry about these for sig figs. Like, you can't count this as 2 because it's not a measured quantity. So we're going to have 3 sig figs in our answer. So our answer is going to be V2 equals 19, and that would be 57 rounds to 60 liters.